I think, probably 2 years before that, it became clear to me that supervised learning is what's going to get us the traction.
Mm-hmm.
And I can explain precisely why. It wasn't just an intuition. It was, I would argue, an irrefutable argument, which went like this. If your neural network is deep and large, then it could be configured to solve a hard task. So that's the key word, deep and large. People weren't looking at large neural networks. People were, maybe studying a little bit of depth in neural networks. But most of the machine learning field wasn't even looking at neural networks at all.
Mm-hmm.
They were looking at all kinds of Bayesian models and kernel methods, which are theoretically elegant methods, which have the property that they actually can't represent a good solution no matter how you configure them. Whereas the large and deep neural network can represent a good solution to the problem. To find the good solution, you need a big data set, which requires it,
Mm-hmm.
and a lot of compute to
Mm-hmm.
actually do the work. We've also made advanced work, so we've worked on optimization for a little bit. It was clear that optimization is a bottleneck, and there was a breakthrough by another grad student in Jeff Hinton's lab called James Martins. And he came up with an optimization method which is different from the one we are using now, some second order method. But the point about it is that it's proved that we can train those neural networks,
Mm-hmm.
because before we didn't even know we could train them.
Mm-hmm.
So if you can train them, you make it big, you find the data, and you will succeed.
Mm-hmm.
So then the next question is, well, what data?
Mm-hmm.
And an ImageNet data set. Back then it seemed like this unbelievably difficult data set.
Mm-hmm.
But it was clear that if we were to train a large convolutional neural network on this data set, it must succeed if we just can have the compute.
And right at that time,
GPUs came
you
out.
and I, our history and our paths intersected, and somehow you had the observation that a GPU, and at that time this is our couple of generations into a CUDA GPU, and I think it was GTX 580 generation. You had the insight that the GPU could actually be useful for training your neural network models. What was that? How did that day start? Tell me. You never told me that moment. How did that day start?
Yeah. So, the GPUs appeared in our lab, in our Toronto lab, thanks to Jeff, and he said we should try these GPUs, and we started trying and experimenting with them, and it was a lot of fun, but it was unclear what to use them for exactly. Where are you going to get the real traction? But then, with the existence of the ImageNet dataset, and then it was also very clear that the convolutional neural network is such a great fit for the GPU.
Mm-hmm.
So it should be possible to make it go unbelievably fast, and therefore train something which would be completely unprecedented in terms of its size. And that's how it happened. And, very fortunately, Alex Krzyzewski, he really loved programming the GPU, and he was able to do it. He was able to code, to program really fast convolutional kernels, and then train the neural net on the ImageNet dataset, and that led to the result. But it was like
it shocked the world. It shocked the world. It broke the record of computer vision by such a wide margin that it was a clear discontinuity.
Yeah. And I would say it's not just like, there is another bit of context there. It's not so much like when we say break the record, there is it's like, I think there's a different way to phrase it.
Mm-hmm.
It's that data set was so obviously hard and so obviously outside of reach of anything. People were making progress with some classical techniques, and they were actually doing something. But this thing was so much better on a data set which was so obviously hard. It's not just that it's just some competition. It was a competition which, back in the day,
wasn't an average benchmark.
It was so obviously difficult, so obviously out of reach, and so obviously with the property that if you did a good job, that would be amazing.
Big bang of AI. Fast forward to now, you came out to the Valley. You started OpenAI with some friends. You're the chief scientist. Now, what was the first initial idea about what to work on at OpenAI? Because you guys worked on several things. Some of the trails of inventions and work you could see led up to the Chat GPT moment. But what were the initial inspiration? How would you approach intelligence from that moment and led to this?
Yeah. So obviously, when we started, it wasn't 100% clear how to proceed. And the field was also very different compared to the way it is right now. So right now, we already used to, you have these amazing artifacts, these amazing neural nets who are doing incredible things, and everyone is so excited. But back in 2015, 2016, early 2016, when we were starting out, the whole thing seemed pretty crazy. There were so many fewer researchers, like 100, maybe there were between 100 and 1,000 times fewer people in the field compared to now.
Yeah,
like
true.
back then, you had like 100 people. Most of them were working in Google/DeepMind, and that was that. And then there were people picking up the skills, but it was very, very scarce, very rare still. And we had two big initial ideas at the start of OpenAI that had a lot of staying power, and they stayed with us to this day. And I'll describe them right now. The first big idea that we had, one which I was especially excited about very early on, is the idea of unsupervised learning through compression. Some context. Today, we take it for granted that unsupervised learning is this easy thing. You just pre-train on everything and it all does exactly as you'd expect. In 2016, unsupervised learning was an unsolved problem in machine learning that no one had any insight, any clue as to what to do.
That's right.
Jan LeCun would go around and give talks saying that you have this grand challenge on supervised learning. And I really believed that really good compression of the data will lead to unsupervised learning. Now, compression is not language that's commonly used to describe what is really being done until recently, when suddenly it became apparent to many people that those GPTs actually compress the training data. You may recall the Ted Chiang New York Times article, which also alluded to this. But there is a real mathematical sense in which training these autoregressive generative models compress the data. And intuitively, you can see why that should work. If you compress the data really well, you must extract all the hidden secrets which exist in it. Therefore, that is the key. So that was the first idea that we were really excited about. And that led to quite a few works in OpenAI, to the sentiment neuron, which I'll mention very briefly. It is not, this work might not be well known outside of the machine learning field, but it was very influential, especially in our thinking. This work, like the result there was that when you train a neural network, back then it was not a transformer, it was before the transformer.
Right.
Small recurrent neural network, LSTM, to those who remember.
The sequence work you've done, I mean, this is some of the work that you've done yourself, yeah.
So the same LSTM, with a few twists, trained to predict the next token in Amazon reviews, next character. And we discovered that if you predict the next character well enough, there will be a neuron inside that LSTM that corresponds to its sentiment. So that was really cool because it showed some traction for unsupervised learning, and it validated the idea that really good next character prediction, next something prediction, compression, has the property that it discovers the secrets in the data. That's what we see with these GPT models, right? You train, and people say it's just statistical correlation. I mean, at this point, it should be so clear to anyone.
That observation also, for me, intuitively, opened up the whole world of where do I get the data for unsupervised learning. Because I do have a whole lot of data. If I could just make you predict the next character, and I know what the ground truth is, I know what the answer is, I could train a neural network model with that. So that observation and masking and other technology, other approaches, open my mind about where would the world get all the data that's unsupervised for unsupervised learning.
Well, I think so. I would phrase it a little differently. I would say that with unsupervised learning, the hard part has been less around where you get the data from, though that part is there as well, especially now. But it was more about, why should you do it in the first place? Right. Why should you bother? The hard part was to realize that training these neural nets to predict the next token is a worthwhile goal at all. That was
that
the
it
goal.
Would learn a representation, that it would be able to understand.
That's right. That it will be useful.
Grammar and
But but it just wasn't obvious.
Right.
So people weren't doing it. But the sentiment neuron work, and I want to call out Alec Radford as a person who really was responsible for many of the advances there. The sentiment, this was before GPT-1. It was the precursor to GPT-1, and it influenced our thinking a lot. Then the transformer came out, and we immediately went, oh my God, this is the thing. And we trained GPT-1.
Now, along the way, you've always believed that scaling will improve the performance of these models.
Yes.
Larger networks, deeper networks, more training data would scale that. There was a very important paper that OpenAI wrote about the scaling laws and the relationship between loss and the size of the model and the amount of data set, the size of the data set. When transformers came out, it gave us the opportunity to train very, very large models in very reasonable amount of time. But did the intuition about the scaling laws of the size of models and data, and your journey of GPT-1, 2, 3, which came first? Did you see the evidence of GPT-1 through 3 first, or was it the intuition about the scaling law first?
The intuition. So I would say that the way I'd phrase it is that I had a very strong belief that bigger is better, and that one of the goals that we had at OpenAI is to figure out how to use the scale correctly. There was a lot of belief in OpenAI about scale from the very beginning. The question is, what to use it for precisely? Because I'll mention, right now we're talking about the GPTs, but there's another very important line of work which I haven't mentioned, the second big idea. But I think now is a good time to make a detour, and that's reinforcement learning. That clearly seems important as well. What do you do with it? So the first really big project that was done inside OpenAI was our effort at solving a real-time strategy game. And for context, a real-time strategy game is like, it's a competitive sport.
Yeah, right.
Where you need to be smart, you need to have you need to have a quick reaction time, there's teamwork, and you're competing against another team. And it's pretty involved. And there is a whole competitive league for that game. The game is called Dota 2. And so we trained a reinforcement learning agent to play against itself, to produce, with the goal of reaching a level so that it could compete against the best players in the world. And that was a major undertaking as well. It was a very different line. It was reinforcement learning.
Yeah, I remember the day that you guys announced that work. And this is by the way, when I was asking earlier about there's a large body of work that have come out of OpenAI. Some of it seemed like detours, but in fact, as you're explaining now, they might have been detours, seemingly detours, but they really led up to some of the important work that we're now talking about, ChatGPT.
Yeah, I mean, there has been real convergence where the GPTs produce the foundation, and then reinforcement learning from Dota morphed into reinforcement learning from human feedback.
That's right.
And that combination gave us ChatGPT.
There's a misunderstanding that that ChatGPT is in itself just one giant large language model. There's a system around it that's fairly complicated. Could you explain briefly for the audience the fine tuning of it, the reinforcement learning of it, the various surrounding systems that allows you to keep it on rails and let it give it knowledge and so on and so forth?
Yeah, I can. So the way to think about it is that when we train a large neural network to accurately predict the next word in lots of different texts from the internet, what we are doing is that we are learning a world model. It looks like we are learning this. It may look on the surface that we are just learning statistical correlations in text. But it turns out that to just learn the statistical correlations in text, to compress them really well, what the neural network learns is some representation of the process that produced the text. This text is actually a projection of the world. There is a world out there, and it has a projection on this text. And so what the neural network is learning is more and more aspects of the world, of people, of the human conditions, their hopes, dreams, and motivations, their interactions and the situations that we are in. And the neural network learns a compressed, abstract, usable representation of that.
Mm-hmm.
This is what's being learned from accurately predicting the next word. And furthermore, the more accurate you are at predicting the next word, the higher the fidelity, the more resolution you get in this process. So that's what the pre-training stage does. But what this does not do is specify the desired behavior that we wish our neural network to exhibit. You see, a language model, what it really tries to do is to answer the following question. If I had some random piece of text on the internet which starts with some prefix, some prompt, what will it complete to? If you just randomly ended up on some text from the internet. But this is different from, well, I want to have an assistant which will be truthful, that will be helpful, that will follow certain rules and not violate them. That requires additional training.